Okay, welcome back to another video lecture for calculus. And this video is designed to support a calculus course that I'm teaching this semester. And in this video, we're going to be looking at section 1.4, part 1. And I should mention that 1.4 is broken up into probably about 3 parts because the concepts that we cover in 1.4 are extremely fundamental to the rest of the calculus course. And if you don't know these concepts very, very well by memory, and when they apply, then you're not going to be much use in the rest of the course. Almost everything that we do will not involve very, very simple derivatives like the ones that we have looked at so far. So I want to establish what these properties that derivatives have that we must learn, memorize, and follow at all times throughout the course are. So section 1.4 part 1 is going to establish 2 kind of almost trivial properties. Once you see how they work, you'll say, okay, well that makes sense and probably didn't really need to be proved. But then we're going to talk about an extremely important concept, which is what do you do when you have functions like the quadratics that we saw in, say, Algebra 2 or college algebra that contained multiple x variables. And you can take a guess about how these work, and you'd actually probably be right about that guess, but I think it's important that we look at that in some detail so that we know precisely why that is the case. Okay, so to start with, I've just got 2 quick refresher exercises. We know how to take derivatives of nice objects that involve x to the power of something, and we've established at this point that it applies when the exponent is a natural number and when the exponent is a rational number. And to a certain extent, we've hinted at the fact that it might apply when the exponent is even a negative number, and it turns out that that is correct. There will be a supplemental video on that particular rule after we've established the final rule in section 1.4 in video titled part 3. And what we're going to do is we're going to derive the rule using the general power rule, and then we're also going to use the quotient rule, which is what 1.4 part 3 will be over, to prove that that result is true. So things like this, we now have seen a result and a proof. We know how to do this just by writing the answer down. Power drops out in front. New power is 1 less. X to the 7th, power drops out in front. New power is 1 less. Boom, we're done. So what do we do when we start including constants in the mix? And what I mean by constants is either a constant that is being combined linearly with like a plus or minus symbol, or a constant multiple in front of one of these expressions that we know how to take the derivative of. So what I'm going to do is I'm going to work these 2 problems the long way, and that will give us some information. It's not necessarily a proof, but I think you'll see that any problem that we do this way will follow the same general principles. The same moves are happening every single time. So without going into necessarily like a proof, we're going to show that this must be the case every time we have a constant that's been added, and then every time we have a constant that's been multiplied. So to take the derivative of an expression like x squared plus 2, again, remember that the thing that we're increasing with the little small increase called dx is always the independent variable. It doesn't actually have anything to do with increasing the constant by a certain amount, because the derivative process wants dy over dx, which means we have to give the independent variable a small increase and we have to give the dependent variable a small increase, but this constant on the end does not need to be increased by anything necessarily, because it's not a variable quantity. It's exactly that, it's a constant. So what we can write down is basically the same thing that we have written down before. It's just that we have this added constant on the end. We give the independent variable a small increase, corresponds to a small increase in the dependent variable. We FOIL this expression out or expand it. We ignore terms that are effectively 0. And now the same moves that we did before, where y is defined as x plus 2. So if we subtract y from both sides, that's like subtracting x squared plus 2 from the right-hand side. So we subtract an x squared and we subtract a 2 over there on the right-hand side. Okay, so that's going to leave us with 2x dx is equal to dy, and then dy over dx is equal to 2x. And you'll notice that that's actually the same derivative as this example problem, because the variable portion of the expression is the only thing that affects the derivative. If you recall from like an algebra course, and I'm not going to draw this, but we'll just quickly discuss it so that we can get our head behind what's happening here. The x squared portion of the expression is what governs the shape, that parabola shape that the expression is going to make. If we add or subtract a constant on the outside of whatever the original f of x was, so like in this case f of x could be x squared, so x squared plus 2 is just f of x plus 2 on the outside of the f of x notation. And that corresponds to an up or down movement on the graph. So we haven't changed the shape at all, which means we haven't changed the derivative at all. The only thing we have done is we have moved where that function is in space, but it doesn't change the nature of the derivative because it doesn't change the shape of the graph. Okay, so what that implies for us is that whenever we have constants on the end, plus 2, minus 1, minus 7, plus 8, plus a half, plus 3/3, 3/5, something like that, anything like that, we can just drop them off according to the general power rule. They just don't affect the derivative at all, so they get ignored kind of the same way that the dx squared, dx to the third, and so on gets ignored. And we're not really ignoring it, it's just that the constant becomes a 0 in the derivative because it gets subtracted away every single time. So this thing has the same derivative as the first example problem. Now, if we wanted to look at the constant multiple situation where I have x to the third, which I know how to take the derivative of, and then I've got a times 8 here, you can kind of guess what's going to happen there as well. But in this case, the constant doesn't just drop off. It doesn't 0 itself, because if this were to 0 itself, notice that this is 0 times something, so our derivative would just be 0. It wouldn't be conclusive. And we also know that that can't be the case because these functions clearly produce functions of 1 degree smaller that is their derivative. So if I follow kind of a similar procedure, that is that y plus dy will equal to x plus dx to the third power times 8, well then we notice here that the x plus dx value, when expanded out, gives us x to the third power, 3x squared dx, 3x dx squared, dx to the third power. And then we have our y plus our dy over here on the left-hand side. Okay, well then we have this distributive action where the 8 is being distributed over all of the terms. But remember that the 8 distributing to the dx squared, dx to the third term, we just ignore those because they 0 themselves. That will leave us with 8x to the third as expected, plus 24x to the second dx, y plus dy. And of course subtracting y, remembering that y is defined as, and I forgot to write it down, but y is defined as 8x to the third, and I'm sure we're familiar with that step by now. That's like subtracting 8x to the third from the right-hand side, and all the normal expected cancellations happen. That leaves us with dy by dx is 24x to the second. Now you might also notice that that result is precisely our constant multiple 8 times 3x squared, which is what we know the derivative of x to the third to be. So what that kind of alludes to is that in the case of a constant multiple, it won't just be 3x to the second, it will scale the derivative as well. And you can think about that because in Algebra 2, when we multiply a function like f of x by something in front, that does change the shape of the graph. If you have like an x squared graph, you have this parabola. Okay, well when you multiply it by a number, it gets narrower. It does actually change the shape of the graph, and therefore it does affect the derivative. Now, what we might want to write here is that we could pick any number to multiply that by, and the result would just be 3x squared scaled by that number. In other words, if we want to revise our general power rule to include the possibility of there being a constant, what we do is we multiply the coefficient times the power. In other words, the power drops down just like it did before, but it multiplies whatever number is here. 3 times 8 is 24, and then we drop the power by 1 just like we did before. So we'll have n times a times x to the power n minus 1, and this is an updated version of our general power rule. Okay, so now that we know what to do with constants and constant multiples, it should be very easy to take a ton of new derivatives very, very quickly. But we still have one other situation that we would like to look at. What about the case where we want to find the derivative, that is, find f prime, for something that looks like this? And this is a little bit different because we have multiple x variables in this expression to begin with instead of just a single x variable like all of our previous examples have had. So if you think about this, there's a couple of ways that we could choose to do this. What I could do is I could call this part here to be u. In other words, I'm setting x squared equal to some variable, or just I've given it a different name for a part of a function, and I'm calling it u. And I could take this portion here and give it a different name. I can call it v. And then our f of x is actually u plus v. But here we've written that u is equal to x squared and v is equal to 2x plus 1. And so we know that if I were to increase x by a small value dx in this case, then u would increase by a small value du. So what will happen when I take the derivative here is we'll have that y is equal to u plus v. Increasing the x value by a small value dx will correspond to u being increased by a small value du. And of course we have to make sure that since this is one equation here, that we do the same thing to all parts of the equality to make sure that we have preserved that equality. So if I increase the x by dx here, since v is also a function of x, I must increase x by the same dx there. If you increase x by dx in the expression v, then v will increase by dv, a small increase to the v variable. So what that will correspond to is we will end with this expression here. But notice that when I subtract y, which at this point y is defined by u plus v, that's like subtracting both u and v from the right hand side. In other words, dy is equal to du plus dv. But remember that the original thing that we want to do is increase the x value by that small value dx. So if I divide this entire expression by dx, just everything in here gets divided by dx, notice that what we have is actually a statement of how to find what the derivative of this thing actually is. Dy dx is the first derivative that we're looking for, and du dx is just a differently named derivative, and dv dx is also a differently named derivative. What it says to do, in other words, this bottom thing right here, this is like our formula. It says that we just take the derivative of u, which we know would be the du dx quantity, that's 2x, and then we take the derivative of v dv dx, which will give us just 2, and we assemble them together by addition. So we just take the du dx, which is 2x, and we take the dv dx, which is 2, and we add them together. The total derivative here, f prime, will just be 2x plus 2. And there's some important notices here. If you had just applied the general power rule to x squared, you'd get the 2x part. If you had just applied the general power rule to 2x, you'd get the 2 part. And if you applied the general power rule to 1, poof, it's gone, it's a 0. So you can just go piece by piece through the original function to find the derivative. And I think this is a really important statement to make, is that the derivative, when you have just a single expression, and you notice that these are combined with linear operations, what I mean by that is they're just added or subtracted. There's no crazy multiplications or exponents or weird types of square roots or like sines and cosines and stuff like that. There's no weird things happening here. It's just like an x squared and plus or minus something else, and then another term that involves x plus or minus something else, and then another term, and so on and so forth. The thing that we have established here is that the derivative is linear. And by linear, I mean that when you have functions combined in a linear way like this, with pluses and minuses, no multiplications or anything, you can just do the derivative piece by piece to get your answer. And we can do a similar sort of argumentation where you have like x squared minus something, and you would see that this works pretty much the exact same way. The end result is that whatever symbol you see here, that is what will happen in the derivative. If I change this to x squared minus 2x plus 1, well then what will happen is in the derivative, the x squared derivative is 2x, the 2x derivative is 2, and so since I have a minus here, I just minus in the middle, and that is my derivative. It's a very, very important property, the linearity of derivatives. And now we know what to do with constants when they're added to the end, or constants when they are multiplied. Now it's worth saying here that that constant multiple rule is actually a rule that has a name to it. And the reason why it is important is because when we have things that are multiplied in front of a expression that we know the derivative of, like x to the 8th, then we can just take that constant multiple off, write the derivative of x to the 8th, which is 8x to the 7th, and then multiply that by the constant after we've done the derivative portion of the process, and that greatly simplifies our life in certain cases.